Okay, today guys, we're going to talk about exponential applications. This is where this applies to real world situations, word problems. There are four formulas that we're going to be using. You should be familiar with them from your previous math classes, but I'll review what these things are. You have a growth equation and a decay equation, and we discussed those graphs yesterday, where the growth graph was an uphill graph and the decay graph was a downhill graph. And here we have 1 plus the rate, and here we have 1 minus the rate. That's the main difference between those two. When you move down to compounding growth, this is what happens with money in like a bank situation. So your rate over here is divided by n, and the exponent is n times t. Down here I tell you what each of these variables mean. So n is meaning how many times a year that money is compounded. And so something like annually would only be compounded once a year. Semi-annually would be compounded twice. Quarterly would be compounded 4 times a year. Monthly 12 times per year. So you could, daily would be 365. So you could use those numbers. The quarterly would be 4 times a year, so your n would be 4 in these spots. So you have to know those words, what they mean, what number is associated with them, and then plug that in. Continuous growth is basically thinking like computer-generated type of growth, where they're continuously adding on the interest into your money instead of waiting until the end of the month or the end of the quarter to calculate that. So this situation, the E is that number E on your calculator, the 2.7 and so on with the decimal number, because lots of things in the world follow that pattern. That's a common number used in exponential things. So again, R is going to be your rate. You need it as a decimal. So instead of, like if you were using 25%, instead of 25, you would need 0.25. 3% would be 0.03. So you're moving the decimal place twice from the percentage. Again, N is the number of times compounded in a year. T is where you plug your time in. And then we get to A and P. A is the ending amount. That's usually your answer that you're trying to find, but sometimes they give you that and you're trying to find something else. P is your starting amount. I use P, even though some books use some different letters, just because P is, in money, is the principal, which means the starting amount. If you pay on your principal for your mortgage, your house, your loan, you're paying on that original debt. So P is a starting amount. Okay, so this is our first example. It is where we have $9,000 and we're investing it at a rate of 2.5% compounded annually. Find the balance after 5 years. So if it's compounded annually, that's just once per year. You can actually just use the regular growth formula. So if you look at that, our ending amount is what we don't know. Our starting amount is 9,000. And then we do 1 plus our rate as a decimal, which it's already a decimal. Some of you might be like, okay, but it's still a percentage. So I need to move that decimal 2 more times to the left to get my rate as a decimal. So it will be 0.025. And then our time is 5 years. So if we had the ends would be 1. You would be dividing by 1 here and multiplying by 1 here. And so those aren't really affecting this. That's why you can use a growth equation instead of having to worry about the compounding. Again, that's because the annually means the n is 1. Here, you just plug it into your calculator. Hopefully you type it in correctly. You might want to pause and type that in, see if you get the same thing I do. When I plugged it in, I got $10,182.67. Okay, for our second example, we're going to use $4,000 We're going to invest it at 5.25% compounded monthly. Find the balance after 6 years. So again, 4,000 is going to be our P. It's our starting amount. Here's our rate, which we will need to change to a decimal. And then it's compounded monthly. So that means our N is 12. Again, we're using 6 years, so that is going to be our time. I'm trying to find the ending amount, so I'm going to leave that as A. My starting amount is $4,000. I'm going to put that in for the P. We're compounded more than once a year, so I need to go to the compounded formula, and I'm going to use my rate as a decimal, so 0.0525 divided by the number of times we're compounding per year, which would be 12. And then my time would be 12, that N again, times 6. So again, I'm just, and you might want to put parentheses, I need to multiply those, and I need to make sure I get that in the calculator correctly, divided. But it's a typing in the calculator situation. You're not having to solve anything too hard, so you might want to pause and make sure you type in and get the same thing I do. When I solved, I got $5,477.27. Okay, so this is supposed to be our third example. We have $12,000 and we're investing it at 3%. So this would be our P and our R once we change it to a decimal. We want to find the balance after 4 years if interest is compounded, A quarterly and B continuously. So we really have two problems here. The quarterly means 4 times a year, so our N is 4. The continuously means we have to use a totally different formula. We have to use the continuous compounding formula or the PERT formula. So I'm going to start with A, and we're trying to find that ending amount. Our starting amount is 12,000, and we're compounding quarterly. So 1 plus, on top of the fraction, 3%, move the decimal twice, you get 0.03. On the bottom is our N, which is 4. And then our exponent would be 4 times our years, which is also 4. And that's how we get it. Now, when I plug that into my calculator, and you may want to pause again, you get 13,523.91. For part B, we're doing the same stuff, but we're going to compound it continuously, so like a computer-generated compounding situation. All right. Our ending amount is going to equal our starting amount, again, $12,000, but instead of the parentheses, we're going to put E. Our rate as a decimal will be the exponent times the time of 4 years. You want to plug that in your calculator, and this gives you 13,529.96. What you will notice is that the two numbers are really close, but this one is more. The continuous compounding is always going to be more than compounding any other way. Obviously, it's going to be closest to daily or by the minute if that is something that you wanted to calculate. But your continuous compounding will always be bigger and would be the best case scenario if you wanted to earn more money. Okay, for our last example, I wanted to use a chemical substance type situation because I'm sure in some of your science classes you deal with half-lives and things like this. So the questions may follow along this type. They're not always money. So this one says the amount of radioactive strontium present after T years is Y equals 10 times 1/2 to the T over 29. And the first question is, what is the initial mass? Well, this type of formula follows what we've been doing with the money, and your starting amount is always right here in front. And so our initial mass will be 10, and let's just say that we had more information. I'm going to give it some units. Typically, we would measure something like this in grams or milligrams or something like that. So I'm going to say we have 10 grams to start with. Then the question is, how much is left after 80 years? Well, 80 years is a time, and therefore you just need to plug it into t. So we have y equals 10 times 1/2 to the 80 over 29. Again, when you type this in your calculator, be careful with the fractions. Make sure you have this one in parentheses. Make sure that when you go to the exponent, that you get all of this in your exponent. You may want to pause and type it in. And my answer came out to be 1.48, which, since I'm using grams up here, I'm going to say it's grams down here. So 1.48 grams. And that makes sense with our situation. So this is the end of your notes and explanation. You can see me for the assignment.